Okay, so advice on homework 26, conservation of energy. In every single one of these problems, I'm going to be using the very same equation to solve it, the law of conservation of energy, which says that I have a certain amount of initial energy plus or minus some work done is equal to the final energy. I'm familiar with that. So I have to take that equation and custom make it to each one of these situations that I have in these 10 problems. So with what minimum speed do I toss a ball straight up to hit the roof of the gymnasium if I release the ball from 1.3 meters above the ground? So here is my application of the law of conservation of energy in this case. The initial energy plus or minus the work is equal to the final energy. There is no work being done by non-conservative forces here. Nobody's pushing or pulling. There's no friction. There's no viscous drag. There's no rocket motors running. All that's acting here is the force of gravity, and gravity is conservative. So when it comes to the initial energy on the left-hand side, I start with kinetic energy because I'm throwing the ball. I also have a little bit of gravitational potential energy because the ball is 1.3 meters above the floor. And I'll choose the floor to be 0. Then, on the right-hand side of the equation, the ball goes up to the roof, and I'm going to have it go just like when we did free fall, sort of kinematics. Go there so that the final velocity is just 0, which means the only kind of energy it has at the end is gravitational potential energy, and then the only thing unknown in my conservation of energy equation is the initial velocity, which I can solve for. How fast do you have to throw it? In the second part of the problem, we let the ball fall from that height back to the ground again. And so I'm going to apply the law of conservation of energy again, except this time I'm going to start high where I have gravitational potential energy, and I'm going to fall and have kinetic energy when I reach the floor. Now the height of the floor is 0, so there's no gravitational potential energy at the end, the ball falling all the way to the floor. The second problem here, what minimum speed does a puck need to have to make it to the top of a ramp? So it starts out with some kinetic energy. As it goes up the ramp, that kinetic energy is transformed into gravitational potential energy. So when I apply the law of conservation of energy to this, I start with the initial energy, which is just kinetic at the bottom. There's no work done by non-conservative forces. I'm told that the ramp is frictionless, so there's no friction acting. The energy that I have at the top is gravitational potential energy, but you have to be careful. They tell me in the problem the distance up the ramp and the angle of the ramp. Sure, the gravitational potential energy at the end is mgh, but I have to do a little trigonometry realizing that h is d times the sine of theta. Once I've written my conservation of energy, once again, the initial speed is the only unknown in the equation. And also, look, the masses cancel. So they tell me the mass of the puck, but it's not needed to solve the problem. Anyway, solve for that initial velocity. Question 3. Car is parked at the top of a hill. And it slips out of gear and starts to roll down the hill. How fast will it be going at the bottom of the hill? Well, at the top of the hill, it starts out with gravitational potential energy, mgh0. And it finishes up at the bottom of the hill with kinetic energy. So as it goes from the top of the hill to the bottom of the hill with no work done by friction, it says ignore friction in the problem. So there's no non-conservative work done. Engine of the car is not running, no viscous drag, no rocket motors, nobody pushing, pulling, no friction. Then the gravitational potential energy it has at the top of the hill, mgh, is equal to the velocity that we'll have at the bottom of the hill, or well, the kinetic energy it has at the bottom of the hill, 1/2 mv squared. Solve for v. Notice once again that the masses cancel, and here they did not give me the mass of the car, so it's a good thing there's a mass on each side of the equation. Question number 4. There's an airplane that's going to land on an aircraft carrier, and the aircraft carrier is too short for the plane to come to a complete stop with just its brakes. So they use a big spring to catch the plane and to bring the plane to rest. So this plane has kinetic energy. It's flying along with some velocity when it reaches it, and then the plane gets stopped by a spring. So initially, it has kinetic energy. There's no work done by non-conservative forces. There probably would be friction involved, but they're telling me I can ignore any of that. And so that's equal to the final spring energy. So what's happening is the kinetic energy of the plane is being transformed into spring energy in the spring, according to the law of conservation of energy. Notice that the masses don't cancel in this case, but that's okay because they gave me the mass of the plane. So I can simply solve for the initial velocity of the plane when I know the stretch of the spring and the spring constant in newtons per meter. We have a fireman. It's going to go down a fire pole. He has gravitational potential energy, becomes kinetic energy, but this is the first problem where work is done by non-conservative forces. There's friction in the pole. So as he goes from having gravitational potential energy at the top to kinetic energy at the bottom, he loses some energy. The energy is lost because there's negative work done by friction. What is friction rubbing together creates heat. So when the question asks about the thermal energy created during the process, it's the heat of being produced by friction that is removing energy from the system. So he starts out with gravitational potential energy, mgh, loses some to thermal energy, and then has kinetic energy when he reaches the bottom of the pole. He doesn't have any gravitational potential energy at the bottom because when he reaches the bottom of the pole, his height is 0. So this is my law of conservation of energy, and in the problem statement I'm given every number that I need in order to make this work out right. Solve for Q. Problem number 6. I have a hockey puck. It was given this initial speed, so it has some kinetic energy. But there's friction, and the friction is going to slow the puck to rest. The statement of the problem says use conservation of energy to do this, because this is a problem I already know how to solve. I have an initial velocity, I have a friction force that causes an acceleration, and then I can use a kinematic equation like v squared is equal to v naught squared plus 2a delta x to solve the problem. Well, here it is conservation of energy style. The hockey puck has kinetic energy, 1/2 mv squared, which I can calculate. Friction removes that energy until the hockey puck comes to a stop. Well, when the hockey puck comes to a stop, it doesn't have any energy at all. So the final energy of the system is actually 0. Now, what we're trying to work out here is what is the distance that it traveled? Well, by using my conservation of energy, I can get my work done by friction. But the work done by friction is the force of friction, which is negative mu mg. We'll flash back to Newton's laws there, where it's mu times the normal force, and the normal force is equal to mg in this case, multiplied by the displacement, which is the distance traveled that we're looking for in this case. I could take this expression for the work done by friction and plug it into my conservation of energy equation and then solve for delta x, or, if you like, use the conservation of energy equation to calculate how many joules of work is done by friction, and then use that to calculate delta x. Either way, the work done by friction is related to the distance the puck slides in coming to rest. Problem number 7 is probably the most complicated one in the assignment. Here I have some winter tubing that's going on. And I'm in a tube, and at constant speed, I'm going to get pulled up this mountain. I'm getting pulled up by a rope that exerts a force and therefore does work. So when I write the conservation of energy, I have 2 really important things going on. I have positive work being done by the rope that pulls me up the incline. And I have thermal energy being generated, which is removing energy from the system. So when I write the conservation of energy, it looks like this. I have kinetic energy to start with and kinetic energy to finish with. The process happens at constant speed. So this kinetic energy that I have at the beginning and the kinetic energy that I have at the end are exactly equal to each other. which means I can subtract it away from both sides. I didn't even have to write it. The fact that there's kinetic energy doesn't matter in this problem because the kinetic energy doesn't change. It's the same on the left as it is on the right. But here you see, I have some positive work done by the force acting over a distance. That's the 120 meters of the slope. Minus thermal energy, which is what I'm trying to calculate, is equal to the gravitational potential energy, mgh, the height of the slope, which is the 30 meters. So I have all of the numbers to put into this. I'm given the force, I'm given 120 meters of the slope, I'm given the mass, I'm given g, I'm given h. I have everything I need except q. Algebraically solve for q for the answer to the question. Problem number 8, a 16 kilogram child slides down a 3.9 meter high playground slide starting from rest, and her speed at the bottom is 1.5 meters per second. What is the change in the thermal energy to the slide and the seat of her pants? So, law of conservation of energy wise, the initial energy she has at the top of the slide is gravitational potential energy, and she has kinetic energy at the bottom. We have everything we need to calculate those. The thing that we don't know is how much thermal energy is generated along the way. So mgh naught minus q is equal to 1/2 mv squared. Solve for the thermal energy. It's as simple as that. Now another child sliding down a playground slide, but this time sliding at constant speed. And we want to find the kinetic friction force acting on the child. So this is how we're going to handle it. The law of conservation of energy. At the top, the child has kinetic energy. The child has kinetic energy at the bottom, but it's the same kinetic energy, just like in the snow tubing problem. It's the same kinetic energy. So I didn't even have to write it because it doesn't change. I can subtract 1/2 mv squared from both sides and it's gone. What I have is a gravitational potential energy minus the work that is done by friction. Since the kinetic energies are gone, then the work that is done by friction is equal to mgh. And they give me the height, 3.8. So I can calculate how much work that is. Well, that work is the force of friction. Here I used a capital F, but it's the force, which is the force of friction in this case, multiplied by delta x, where delta x is the 7 meters going down the incline. So taking the work calculated from the conservation of energy and dividing by the 7 meters of displacement, I'll get the force of kinetic friction on the child in newtons. Last one. Grocery cart has kinetic energy. It runs into a spring, and that kinetic energy is transformed into spring potential energy. According to the law of conservation of energy, the initial energy, which is kinetic energy, 1/2 mv naught squared, is going to be transformed into spring energy, 1/2 kx squared. Be careful, because the compression is given in centimeters. Obviously, that has to be meters, so I'll use 0.7 meters in the calculation. There's no work done along the way because the spring force, like gravity, is a conservative force. There's no friction, no viscous drags, no rocket motors, nobody pushing. And so there are no non-conservative forces to do work. And so the initial energy is equal to the final energy. The kinetic energy is equal to the spring energy. Mm-hmm.